Morning. My name is Spurti. I am pursuing BTech first year in Tribly department at IAR College. My course title is Matrices and Calculus. My topic name is Jordan echelon forms for linear state and input transformations. Introduction to Jordan echelon forms for linear state and input transformations. Jordan echelon forms for linear state and input transformations combine the Jordan canonical form of state matrix with a block echelon form for the input matrix to simplify the analysis of linear systems under both state and input transformations. This approach classifies that reachable systems by a list of indices that determine the canonical form, which can be helpful in understanding the structure and properties of the system. Foundations. What is row echelon form? Shortcut is REF. The row echelon form REF is a fundamental concept in linear algebra, providing a simplified staircase matrix structure. REF is defined by a staircase pattern where pivot elements descend from left to right. Key properties include all zeros being at the bottom of the matrix. Leading entries means pivots in non-zero row must move rightward relative to row above. So, example for this point is if we have a 0 at the beginning of the second row, in the next third row, we must have two zeros at the beginning. So the zeros should be increased into row wise. Crucially, all entries below the pivots must be 0. This form is critical because it enables the efficient solution of linear systems using back substitution. From REF to reduced row echelon form. Reduced row echelon form shortcut is RREF. Refinement of REF. RREF means reduced row echelon form builds upon REF row echelon form by imposing two additional stricter conditions on pivot entries. Canonical form. The pivot is the only non-zero entry in its entire column, ensuring a unit matrix form for any given initial matrix. Unit pivots. In RREF reduced row echelon form, every leading entry pivot must be equal to 1. So, coming to method, RREF reduced row echelon form is achieved through the systematic process of Gaussian elimination combined with subsequent further row operations. It is also known as Gauss-Jordan elimination. Coming to elementary row operations, tools and tools for transformation, matrix reduction to REF or RREF relies on a set of fundamental transformations that preserve the solution set of linear system. Here we can see three types. One is row swapping, row scaling, and third one is row addition. Interchanging two rows to bring a non-zero entry into a pivot position is known as row swapping. So, interchanging a two rows in a matrix to get a non-zero entry in a pivot position is called as row swapping. And coming to row scaling, multiplying a row by a non-zero scalar to normalize the pivot to 1 is a row scaling. To convert a big number which is not 1 into the one number, we will be multiplying a non-zero number which converts into 1. It is called as row scaling. Now, row addition. Adding a multiple one row to another row to systematically create zero entries below the pivot. To create a zero at the entry of the matrix, of the row matrix, we can we can add another row or subtract, by which it can create a zero in in the place of non-zero element. So, introducing the Jordan canonical form. The Jordan canonical form JCF is a standardized upper triangular matrix representation of a linear transformation that reveals its structure, especially when the matrix isn't diagonalizable. It is a block diagonal matrix where each block, called Jordan block, consists of a single eigenvalue on the main diagonal and ones directly above it on the super diagonal. So, building Jordan blocks systematically. The construction of JCF relies on identifying chains of generalized eigenvectors associated with each eigenvalue. Start with eigenvectors. There are 4 steps. So coming to first step, start with eigenvectors. Find the standard eigenvectors V. Eigenvectors is denoted by V that solve the equation T minus lambda I into V equals to 0, where T is a transformation matrix and lambda is eigenvalue. Next, identify generalized eigenvectors. Extend the search to generalized eigenvectors W so that satisfy T minus lambda I into KW equals to 0, for which K is greater than 1. Sorry, T minus lambda I power k. These fill the null space when geometric multiplicity is less than algebraic multiplicity. Form Jordan chains. Chains of these generalized eigenvectors are constructed and each chains correspond directly to a single Jordan block in the canonical form. Determine block structure. The count and dimension of Jordan blocks are dictated by the relationship between the algebraic and geometric multiplicities of eigenvalues. Coming to Jordan echelon form in linear state and input transformations. Linear state transformations are uses invertible change of basis matrices to move the system dynamics matrix into JCF. This simplifies analysis by revealing invariant subspaces. The Jordan form effectively decouples the system modes, making complex dynamics easier to analyze. Input transformations. These involves transforming the input matrix B to align control effect with simplified system structure. This allows control engineers to more easily design inputs that drive specific system modes. The goal is to simplify the control structure, particularly for the systems with multiple inputs. So, example, transforming a system to Jordan form. Let's see. The process transform a complex system matrix A into its simplest canonical form J using the similarity transform P. So step 1 is eigenanalysis. What is eigenanalysis? Eigenanalysis means to determine all eigenvalues and their corresponding eigenvectors for the system matrix A. And step 2. Step 2 is construct chains. What is construct chains? It is nothing but calculate the necessary generalized eigenvectors to complete the Jordan chains for each eigenvalues. Step 3. Build P. Construct the transformation matrix P by using the Jordan chains as its columns. And coming to the step 4, execute transform. Perform the similarity transformation P inverse A into P equals to J, resulting in the Jordan form J. J means Jordan form. By these 4 steps, we can transform a system to Jordan form. Why Jordan echelon form matters? JCF is not just an abstract mathematical tool. It provides critical insights into core properties of linear systems. Canonical representation offers a standard non-arbitrary form for every linear transformation, regardless of the coordinate system chosen. Coming to stability analysis, eigenvalues, the diagonal elements of J directly determine the system stability, dictating whether it converges or diverges. Observability, Similarly, it aids in determining if the internal states of system can be inferred from the measured output. Controllability. The structure of the Jordan form relative to the input matrix B clearly shows which system modes can be influenced by the control inputs. So, coming to the summary, there are some key takeaways. Row echelon form provide efficient methods for solving linear system of equations. The Jordan canonical form is the essential tool for fully characterizing the geometric structure and dynamics of linear transformations. Mastering JCF is fundamental for advanced analysis in control systems, especially for state and input decoupling. These mathematical forms are the foundation for robust system modeling and controlling design. So, future exploration. What are the future explorations? Explore the transformation of output matrix C within the JCF framework. Practice finding JCF for non-diagonalizable matrices with repeated eigenvalues. Utilize software packages, example MATLAB, Python, to compute JCF and verify manual calculations. Thank you.